Good. Okay, so let me remember. Let's remember what we did, where we left off the last time. I said that we were interested in computing the path integral for the anharmonic oscillator, and we wrote down an expression for the path integral that we wanted to compute. Ke, the Euclidean path integral, it goes from the ground state at time t equals 0 to the ground state again at later time Euclidean time beta. And this was given by the path integral of the Euclidean action. So this path integral is weighted by e to the minus I SE, where SE is the integral from 0 to beta, m over 2 dx by d tau. Tau is a Euclidean time variable, plus some potential, which when we specify that potential, we'll specify which problem we're thinking about. So in this case, we're going to be interested in the anharmonic oscillator. So that's where we left off. Let's pick up from there and see how to solve the problem. So again, I need to emphasize that we've done the heavy lifting in this problem essentially by the standard one-dimensional integral that we've already done. So this is going to be a little bit tedious in the sense that, we know where we're going with this problem, but we just have to do the calculations to get there. The anharmonic oscillator, well, the standard anharmonic oscillator is specified by a potential, which is given by V of x equal to half m, the mass of the oscillator, omega squared, its natural frequency, x squared, plus lambda over 4 factorial x to the 4. So what you can see here is that this first piece in the potential is nothing but a simple harmonic oscillator. So this is the oscillator, okay? And then added to this oscillator is this quartic perturbation. So this anharmonic oscillator, you probably guess there's many different types of anharmonic oscillators out there. Basically, you start off with a harmonic oscillator and you perturb it by some further interaction. So in this case, we're starting off with a harmonic oscillator and we perturb it with a quartic interaction. The problem is that with this quartic term present, this lambda over 4 factorial, and you can guess already that the 4 factorial is there to simplify some factors of 4 factorial that will come from differentiating the x to the 4 a number of times. Again, because we've done this already just now when we computed this integral I of lambda. But with this quartic term present, we're not going to be able to explicitly carry out the path integration. However, we can imitate what we just did with the previous integral and try and compute the path integral perturbatively in the coupling lambda. So lambda is what we call a coupling constant. It's worth writing that down. So this whole term here is a quartic perturbation. And this lambda is the coupling constant. And typically what we do here is we assume that lambda is small and we want to construct a perturbation series in lambda and perturbatively evaluate quantities that we're interested in, things like the propagator or other observable quantities, observable quantities, right? And we'll get an expression in lambda, which will allow us to evaluate term by term the corrections to the harmonic oscillator that come from this quartic perturbation. Okay, so as before, as in the case of the one-dimensional integral that we were considering, we're going to start off by defining some related path integral for the harmonic oscillator coupled to an external source term, which will be interpreted as an external force acting on the oscillator. So to that end, I'm going to define the sourced path integral which I'm going to call K naught, so K Euclidean naught, and this is going to be a functional of J. So this is one of the differences from what we did last time. Last time we had an integral which had some lambda dependence, and then we introduced another integral, A, which had some J dependence. And A was a function of J. So now we have a function of a function. And so we have a functional of J. So this K naught E of J is going to be a functional of some source J, and it's going to be defined as follows. It's a path integral over paths x of tau, weighted by the following exponential. So it's e to the minus the integral over Euclidean time tau of a half m dx by d tau squared plus a half m omega squared x squared minus j x, and j is generally going to be a function of tau times x. And that's going to be closed there. And there. Okay, so this is the object that we want to consider. Now, internal to this object is an integral over tau, this guy here, which I'm going to use to define the Euclidean action. And I'm going to call that S Euclidean naught, which is going to be a functional of J because, it's going to be a functional of X and J because I integrate out the tau dependence, and what's left is a function of tau, and it contains X and J variables. But in fact, I'm going to abuse some notation here and just consider the dependence on J, right? And there's a reason for this. The reason is because I want to draw as strong an analogy with what we did with this one-dimensional integral as I can. So, as in the simple case that we just considered, the one-dimensional integral, every functional derivative of this Ke with respect to J pulls down a factor of x of t. That's because every functional derivative, generalizing going from functions to functionals, every functional derivative acts only on functional derivatives with respect to J act only on this term here. Every time I differentiate with respect to J, I pull down a factor of x because I get, two minus signs. And then I can add some coefficients to this and resum this to whatever functional I'm thinking of. The upshot here is that I have an expression now, I will have an expression for what we called previously, or what some authors call the fundamental relation in quantum field theory. So we can show then that with some small assumptions that the following is true, that any functional of the functional derivative with respect to j acting on this k e naught of j is the path integral with respect to x of that same function, only now it's a functional of x of tau, times e to the minus s e naught of j. Okay, so same kind of relation we had previously, except now we are not talking about functions and differentiating with respect to some independent variable. We're talking about functionals and doing functional differentiation with respect to the integration variable in this case. Sorry, with respect to the source, in this case, j, which is a function of tau. Any questions? As usual, I have an exercise for you following from here, which is prove this. It follows in exactly the same way as we had for the previous integral. However, now we can use this and make a particular choice for the function f, functional f. Now, let's choose f of x equal to e to the minus the integral with respect to tau of lambda over 4 factorial times x, remember x is a function of tau, to the 4. Right. So again, x is just a placeholder here, right? I can stick in whatever I want. In particular, I can replace x with the functional derivative, and our fundamental relation then becomes simply that e to the minus the integral with respect to tau of lambda over 4 factorial times delta by delta j, acting 4 times, so to the 4, all acting on k e of j is equal to the path integral of the exponential minus integral with respect to tau lambda over 4 factorial x to the 4 that closes the exponential, e to the minus s e naught of j. Okay. Let's expand this second piece so that we can see what we're dealing with. And if we do that, this is the path integral of e to the minus the integral with respect to tau of a half m x dot squared, where my dot here now means d by d tau, plus 1/2 m omega squared x squared plus this factor of lambda over 4 factorial x to the 4. and then minus the source term jx. And let's close the integral. So clearly, if I evaluate this at j equals 0, I find that I get the following. So k Euclidean 0, beta 0, 0 is e to the minus the integral d tau lambda over 4 factorial delta by delta j to the 4, all acting on k e naught of j, evaluated at j equals 0. Okay, because the right-hand side, this path integral, is exactly the path integral that we want to compute, right, when j equals 0. So basically, we're doing what we did with the one-dimensional integral. This is now the left-hand side. If I do this action of e to the minus the integral of this delta by delta j to the 4, acting on k Euclidean naught at j and evaluated at j equals 0, then I expect to get at least, if I could do this exactly, I would expect to get the Euclidean path integral that I'm interested in. Of course, I can't do this exactly, and so I need to do it perturbatively. And we do exactly what we did previously. We make a Taylor expansion of this exponential. We Taylor expand this exponential by assuming that lambda is small, and then let each term act on the sourced path integral, and we would expect to get, as we did previously, we would expect to get, from the first term, k e naught at j equals naught. From the second term, we would expect a lambda over 4 factorial integral over tau delta by delta j to the 4, acting on k e naught at j, and then evaluated at j equals naught, and then I would expect some high order terms in lambda, so lambda before at least. Okay, so again, philosophically speaking, exactly what we did for the previous case. Nothing particularly deep going on, at least conceptually. All right, and to summarize, if we then know what this functional k e naught of j is, then we can construct an order by order expansion of the propagator, of the Euclidean propagator, k e naught beta naught naught. So it all comes down to knowing whether we can evaluate the functional k e naught of j. Unfortunately for us, we can, because as per usual, we would expect that with a quadratic term only, this would be a Gaussian or some variant of a Gaussian that comes from shifting, for example, which we can figure out by completing the square. Any questions? Okay. So now I want to evaluate this quantity. I want to evaluate this quantity k naught e of j, which, as we said, was this path integral here. Okay, how do we evaluate this path integral? No, sorry, I don't want to evaluate that. I want to evaluate this guy here. All right, so Let's do that. So to evaluate K E naught of J, which is the path integral over X of the exponential minus integral d tau a half m x dot squared plus a half m omega squared x squared minus j x. We're going to do the following. The first thing is we're going to try and split it into a part that involves j and a part that doesn't involve j. The part that involves j is the part that we're really interested in, because remember, we're going to try and functionally differentiate with respect to j. The part that doesn't involve j is actually going to be a path integral. Now, in this case, it turns out that we won't need to know what that path integral is. But in general, that path integral is generally one that we can do. Let me explain what I mean. So suppose we've solved the classical equations of motion. I want to emphasize here that these are the classical equations of motion. The classical equation of motion for this is nothing but a sourced harmonic oscillator. And so you can vary the action, and you'll find that the classical equations of motion are mx double dot equal to m omega squared x minus j. So without the j term, this would just be x double dot equal to omega squared x, which is just the Euclidean harmonic oscillator equations, hence no minus sign, right? But with this j term, there's something on the right-hand side. And this justifies why we call this a source term. Okay, so let's make a note of that. This is why this is a source term. Source or driving term. Okay, so suppose we can solve this this classical equation of motion subject to the boundary conditions as follows. Subject to, so with boundary conditions x at naught equal to x at beta, and I'm gonna impose Dirichlet boundary conditions at both ends, so set it equal to 0. And the solution I'm going to call the classical solution, and label it x classical of tau. So suppose I've solved the classical problem. Okay. What do we do from there? Well, now suppose given that classical problem, I make a change of variables. I'm going to change variables from x of tau to y of tau, which is x classical, sorry, which is x of tau minus x classical of tau. So what you can see here is the y variables are fluctuations around the classical path. So I'm changing from my path that I'm interested in to rewrite the path integral in terms of fluctuations about the classical path. So the classical path optimizes the action, which means that the measure for my path integral, dx of tau, is the same as dy of tau. Because as far as these are concerned, the classical solutions are effectively constants. Okay. With this in play, it follows that the following is true. The integral from 0 to beta with respect to tau of a half mx dot squared, remember dot is d by d tau, plus a half m omega squared x squared minus j of x splits up into two parts. Okay. One part is an integral over d tau, again from 0 to beta, of a half mx dot squared, sorry, classical dot squared, plus I'm just substituting for x now, plus a half m omega squared x classical squared minus j x classical, close that. Right, so that's just the piece involving x classical, plus another part that is it's actually a minus integral from 0 to beta d tau of a half m y dot squared plus a half m omega squared y squared, plus cross terms, which are going to be order y of tau. And as an exercise, I want you to show that those terms, the cross terms, all vanish. In other words, I get no contribution from these guys, which means that my integral, sitting in the exponential of the integrand, in the path integral, splits up into two parts. Notice that the first part is the only part that involves j, whereas the second part contains all the y dependence, which means that when I do a path integral, where my integral measure with respect to x just becomes an integral measure with respect to y, this guy, all of this stuff here, I can pull out of the path integral. Let's put that in writing. But this means that our path integral splits up as two parts. One part is just e to the minus s classical of j, which I pull out of the path integral, times the path integral with respect to y of tau of the following. It's e to the minus integral with respect to tau of a half my dot squared plus a half m omega squared y squared. Do you recognize what this is? See, the nice thing about having only two people in the room is I can call on you individually. Sebastian?
The harmonic oscillator.
It's just the harmonic oscillator, right? Which is exactly what you've just done. So this is just the harmonic oscillator potential, harmonic oscillator path integral. For my purposes, for this part, I am going to call this guy C, because as far as I'm concerned, it is a constant that is independent of J. Okay, so that's all we care about. We just want to isolate the J dependence. So even if I didn't know the answer to this harmonic oscillator path integral, I wouldn't care because it's independent of J, and I expect to factor it out when I'm doing J derivatives. And the remaining piece S classical of J is what I'm defining as the integral of a half m x classical dot squared plus a half m omega squared x classical squared minus j x classical. Okay, so this is the Euclidean action that's evaluated on the classical solution. Let's put this into a better form, because it turns out it can be put into a better form, and all I have to do is integrate by parts. If I integrate by parts, I get the integral over tau of minus a half m x classical double dot plus a half m omega squared x classical minus j all times x classical. Okay, let's make that small, lowercase x classical. So what I've done here is I've integrated by parts, and I've pulled out a factor of x classical on the right hand side. When I integrate by parts, I get this minus sign here, and I get the second derivative, but of course that means there's one x classical left. That's why I'm pulling that out. The square goes away because that's absorbed into that's where that factor comes in from. Is everybody with me?
Yes.
Yeah.
This stuff here from the classical equations of motion is nothing but a half j. So a half j minus 1j gives me the following expression for the Euclidean action. It's much easier to work with than all of that stuff up there. It's just minus a half j, which is a function of tau, x classical, which is a function of tau. Okay, so basically, if we know x classical, then we can work out the derivatives. So what do we use for x classical? So let's solve. I said a little while ago that I'm going to assume that I can solve the classical equations of motion, and if I could solve the classical equations of motion, then I could break up the path integral in that form. So what do we use for the classical equations of motion, for the classical solution?
Sorry, I didn't get this last step.
Mm-hmm.
You have written minus half integral d tau j tau xcl tau.
Yeah.
So how did we get it from the previous step?
So the classical equations of motion, remember, are this. This here.
Are you
so take out a factor of minus a half. Take out a factor of minus a half in these first two terms. You with me?
Are you like writing something on the board? I can't see.
I just have a laser pointer pointing.
Okay, so it's not pointing.
Oh, weird. See, try again. That's strange. Oh.
Okay, I can pull out the half.
No, hold on.
Went away.
Hold on, I see. I gotta reconnect. Sorry, just give me a sec. I seem to have lost connection. AirPlay is unable to do that. Why is AirPlay unable to do that? Stop sharing. Start again. Give me 1 second. Start. Great. Okay, we seem to have lost connection. Just hold on 1 second. I need to try that again. Okay. I'm not sure why, but this is not allowing me to share. Okay. I don't want to stop Zoom. What is it? AirPlay? Oh, I see. Sorry. I'm not connected to the internet. Okay. Let's try again. Not that. Share. AirPlay. Share. There we go. All right. So now you can see. Yes, good. Can you see that?
Yeah.
Okay. So if I take out a factor of a half, in fact, take out a factor of minus a half from here, from the first two terms.
Okay. Yeah, the pointer went away again. Anyways, it's fine. Let's pull out a factor. Oh.
Pointer's gone away again. It's very strange. Okay. Take out a factor of minus a half. What you're left with is basically the classical equations of motion on the left-hand side.
Okay, so, yeah, sure.
Right? And then that's going to give you minus j.
Okay.
Or rather j. And then that factor of minus a half, they will give you sorry, it's going to give you minus j, and the factor of minus half is going to give you a half j. So half j minus 1j is minus a half j. And there's the x classical left behind.
And I have one more doubt from the previous slide. So there was a minus sign in the two terms. I didn't get that one.
A minus sign in the two terms. Where?
The last line, where the order y tau terms going to 0. So there is a minus sign in terms of in front of the y terms.
Okay, so you just have to substitute in. So x classical there is yeah, that might be a plus actually. All right, I'm gonna mark this down as a, for the yellow, it might be a plus. I've got to go check that. But basically, it's either plus or minus. It's a question of how you substitute into the equation. In fact, it's got to be a plus.
And why didn't we get a j term in the y expression?
Sorry?
Why didn't we get that j term? Shouldn't
the
we
y
have
expression?
jy?
The jy term is contained in the cross term. And my statement is the cross terms will vanish.
Okay, got it.
Okay.
Thank you. Yeah.
Okay. Let's see. We're still sharing. Good. So let's go back then. So to solve the equations of motion, the classical equations of motion, I'm going to use the method of Green's functions. Okay, so to solve this, we're going to use the method of Green's functions. As follows. So you know that if I'm trying to solve a differential equation of the following form, oh, no man, this has gone off again. Sorry, I keep losing internet connectivity on my iPad. Okay, you can still hear me though, right?
Yeah.
Okay, so I'm going to describe what I'm going to do, and then we'll finish it. I say we've got 10 minutes left in any event. My iPad is now not picking up the Wi-Fi at all. So let me describe what it is I'm trying to do, and then we'll cover this in the next lecture. So let's stop sharing so we can talk. Right. So the point is, I want to solve this problem using the method of Green's functions. And you know from your first course in differential equations that the Green's function satisfies the same differential equation that x classical does, except instead of the source term j on the right hand side, I replace it with an impulse source. In other words, the Dirac delta function, and it's subject to the same boundary conditions that my x classical would be subject to. So we'll then solve the Green's functions. We'll solve the problem for the Green's function. The Green's function is the classical propagator in the sense that it takes some initial condition and then propagates it forward in time. So we will then construct a solution out of the Green's function and substitute that into the equations of motion. And once we've done that, substitute that into the propagator. And once we've done that, then hold on, I seem to be back. Let's see if I can get us back. once we have that, we'll have a nice expression that we can use okay, there we go. We're going to use the method of Green's function, where the Green's function for this problem satisfies the following differential equation. It's the same differential equation as our original function satisfies, except instead of having j on the right-hand side minus omega squared g of tau, let's call it tau prime, we have a delta of tau minus tau prime on the right-hand side with the same boundary conditions that we imposed on x, namely that g of 0 tau prime and g of beta tau prime both vanish, in terms of which my original solution, x classical of tau, can be expressed as a convolution. So integral from 0 to beta d tau prime g of tau minus tau prime times j of tau prime. So that's my classical solution once I know what the Green's function for the problem is. Okay. And with this classical solution, I can then go ahead and substitute for x classical into the expression that we just found for k naught e of j. And we'll find that k naught Euclidean of j is c, our constant, which is really a path integral in y, times the exponential of a half integral with respect to tau and tau prime of j of tau. That was the original j that we had. And now the x classical gives us a g of tau minus tau prime, j of tau prime, and I integrate with respect to tau and tau prime. And let's close braces there. Okay. Green's function itself is not too hard to calculate. In fact, what we do is in the large beta or low temperature limit, we can do the following. We symmetrize the time interval to run over minus beta over 2 to beta over 2 instead of 0 to beta. We take the beta to infinity limit and we Fourier transform its defining equation. So we can write down an expression in Fourier space and then find the inverse Fourier transform. And we'll have an integral representation for G as the following. G of tau minus tau prime is minus 1 over m, integral from minus infinity to plus infinity, dk over 2 pi with some normalization for our Fourier transform, e to the I k tau minus tau prime over k squared plus omega squared. Let's write better omega. Okay, So that's the Fourier representation, Fourier integral representation for G. And for our purposes, this will suffice for computing the leading order correction to the ground state energy, meaning I don't actually have to do the integral. The integral representation will be enough, and you'll see why in a little bit. But a very worthwhile exercise for you to do is to show this. Again, what you need to do is, we were doing integrals from 0 to beta. You need to symmetrize that interval and integrate from minus beta over 2 to beta over 2. Take the beta to infinity limit and do a Fourier transform, and then solve and then do an inverse Fourier transform. And that'll give you this expression for G of tau tau prime. In fact, you know what? Let me do two things. Let me, exercise 1 is to show this. And exercise 2 is to actually carry out the integral. So the way to do this is to use an appropriate contour in the complex K plane and compute the 0 temperature or beta to infinity Green's function. So find an appropriate contour on the complex K plane and do the K integral to find the full expression for G of tau tau in the 0 temperature limit. Okay. Zero temperature Green's function. Okay, so let's leave it there, and we will pick it up next week, where I will solve this problem and we'll compute the first order correction to the ground state energy of the harmonic oscillator with the quartic and harmonic perturbation.